All right, let me go into 7.4. Hop over here. And again, just like I did with 7.3, there's a video example at the very beginning of 7.4, and that's because it's something I often don't get to do in class because I don't have the time. So I recommend watching it. You can see what I do here. I go through, let me step back here. I give you an integral of a ratio of polynomials. It's a rational function. You integrate a rational function. And then notice I didn't tell you what the coefficients are. So in the video, I say, well, let's suppose the coefficients are 2, 4, 4, and 5. And then we go through and we do work on that. I highly recommend you watch it because it's a review. It's actually a review. It's just a U-sub. But then part B, I change out the coefficients and we do something different. I highly recommend you watch. It's not new. It's just showcasing how you could tackle that problem different ways. And part C, same thing. I'm trading it out for different values. Again, this time, actually, I complete the square. So it's very similar to today's lecture. And then part 4, I trade out again, but I get down to this. And here's just where I want to stop. So part 4, let's suppose you were given an integral of x plus 4 over x squared plus 4x minus 5. A U substitution is not going to work for you. I'm just telling you, it will not work. If you watch the video, I explain why. But a U substitution will not work. The only thing you could possibly do is some algebra. But then you're stuck. Nothing cancels. Nothing does it. You're just done. There's no U substitution that's going to help you, I promise. Completing the square actually might work here. Yeah, completing the square might work, but to motivate a new method, we're not going to complete the square and do a trig sub. Instead, we're just going to mention this right here, that the fraction x plus 4 over the factored x plus 5 times x minus 1 actually is this. So section 7.4 is all about pulling apart a fraction into its component subfractions. The question is, how the heck do I know that the fraction we are given pulls into 1/6 over x plus 5 plus 5/6 over x minus 1? How in the world could you possibly derive that? And that is really, oh, by the way, if you can pull it apart like that, notice it integrates very quickly because that's just 1/6 times the natural log of x plus 5 plus 5/6 times the natural log absolute value of x minus 1. So we can integrate that very quickly as long as we can do some magical algebra that pulls this apart. So the rest of today, very short time, we're going to talk about how to pull that apart. How do we do that taffy pull of pulling apart a single fraction into its component fractions? And the way that I motivate this idea is by looking at a number like 7 over 12. 7 over 12 is just a simple fraction. What we could do is we could factor its denominator. Just like if that denominator was a polynomial, you would factor it. If you factor 12, it factors into 4 times 3, but 4 factors further into 2 times 2. So that's the prime factorization, 2 times 2 times 3. So we could hope that 7/12 could be broken into the sum of subfractions where the denominators are its prime factors, 2, 3, and then 2 times 2. Notice our prime factors are 2, another 2. So we have a representation for the first power of 2 and a representation for the second power of 2, and then 3. And it turns out there are an infinite number of ways to write 7/12 as the sum of these fractions. Here's just one way. 1 and a 1 and a 0. That is one combination of A, B, and C that will give you 7/12. Okay. All right. So how do we do that? Well, before we get into that, we have to mention one thing that's incredibly important, actually. Given a rational function, which is just some polynomial p divided by some polynomial q, and these must be polynomials. Very, very, very important. So I'm going to write that in here. Must be polynomials. Very important. We can express the function f, the rational function, as a sum of simpler fractions, provided one very important condition. The degree of the numerator must be strictly less than the degree of the denominator. So you cannot break a polynomial or rational function down if you have something like 3x squared plus x plus 1 divided by x squared plus 2. You can't break that. That is not what this theorem will let you do. This theorem is saying that a fraction, a polynomial fraction, can be broken into smaller subfractions if the degree of the numerator is strictly less than the degree of the denominator. If that's the case, then it can actually be broken into subfractions. If it's not the case, in other words, if the numerator and denominator have the same degree, and I'll write this down, if degree of the numerator is greater than or equal to the degree of the denominator, do long division. Very important to get that long division done first. Okay. It actually speeds up the process anyway. So, and I have a video example of that, but we'll still see those in lecture as well. All right. So here is partial fraction decomposition, which is the whole point of 7.4. It's all summarized basically right here. Partial fraction decomposition, how to. Given a rational function, a ratio of polynomials only, so important that I'm going to highlight that because I'll often find students that they're faced with some ratio of radicals and they try to do this. That doesn't work. So given a rational expression, a ratio of polynomials only of p of x over q of x, we want to decompose that into simpler rational expressions. This is also known as partial fraction decomposition. So the first step, completely factor the denominator. So that's step one. Just do that. And by the fundamental theorem of algebra from your pre-calculus course, you know that every single polynomial in all of mathematics can be factored into the product of linear and irreducible quadratic factors. So you should be able to factor a polynomial down into the product of linear factors and possibly some irreducible quadratics like x squared plus 5 or x squared plus x plus 1. That's irreducible. You cannot factor that. So every polynomial has a property that it can be factored into the product of linear and irreducible quadratic factors. Then, once you factor the denominator, for each linear factor of the denominator, which might have the form 3x plus 5, and it might even, when you factor it, it might be 3x plus 5 squared, right? You might have a denominator that has a power. That's totally allowable, right? So for every time that you see a linear factor in your factored form of this denominator right here, the decomposed or taffy pulled out, or how that partial fraction decomposition looks, it'll have a term for the first power, even though let's pretend for a second that this was, just pretend that this was the third power. Let's just pretend. Even if it was the third power, you'll still have a fraction that has its first power, a fraction that has its second power, and a fraction that has its third power. That makes this kind of a messy problem. And then same thing for each irreducible quadratic, actually. So for each irreducible quadratic factor of our denominator, and irreducible quadratic has the form ax squared plus bx plus c to the nth, you'll have a series of fractions that look like ax plus b over ax squared plus bx plus c, and then a different linear factor in the numerator over that irreducible quadratic squared, all the way until you get to n of them if you have the nth power in your denominator. You can see in this sentence down below, this how-to is very convoluted. It's best just seen in practice. So if you're staring at this and going, what the heck is he talking about? I don't blame you. It's a very hard thing to say. It's a lot easier to do. So I'm going to at least focus on the steps 1, 2, and 3. We'll come back and talk about step 4 a little bit later. But let's talk about just steps 1, 2, and 3 today. Okay? Because that's the key. All right. So let's go ahead and just do something simple. I say simple, but it looks pretty terrible. Set up the decomposition for the rational expression, but do not try to find the coefficients. So this one example will give you the whole idea of what I just said in the previous page. I already pre-factored the denominator for us. So step 1 on the previous page, which said completely factor the denominator, I've already done. So we're okay there. Now I'm going to look through and I'm going to highlight in yellow all the linear factors. There's a linear factor and there's a linear factor. Let me point arrows at them. Linear, linear. And in maybe blue, if I actually clicked on it, I'll highlight the irreducible quadratic factors. Partial fraction decomposition will take this specific fraction. Notice it's a ratio of polynomials. Often when I do this, I tell students, tilt your paper sideways into landscape mode because it's going to be a lot of handwriting. X plus 1 times the quantity x squared plus x plus 4 to the first, and then x squared plus 3 to the second. And what we're going to do is pull this apart into a bunch of subfractions. This is just like that example where I said 7 over 12. It can be broke into some number over one of its prime factors plus some other number into over one of its other prime factors plus some other number over the second power of this prime factor because it occurs twice. It's the same idea. Our prime factors are all of these. These are our prime factors. So this can be broken into a over x to the first plus b over x to the second plus c over x to the third. Notice I have each power representation of x to a power all the way up to x cubed. Then I say plus some completely different numerator over the next factor, x plus 1. I only need that to appear once because it only has power 1. Then I move to the irreducible quadratics. The irreducible quadratics, their numerators will not be constants. They'll be linears. So the numerators are a degree less than the type of factor you have. This is a linear factor. So its numerator are all constants. This is a linear factor. So its decomposed numerator is a constant. This is a quadratic factor. And so because it's a quadratic factor, its numerator is 1 power less. It's a linear. So I'm going to go ahead and say plus ex plus f. That's a linear. over the irreducible quadratic that we had there, which was an x squared, I can't remember, plus x plus 4. Now we go to the next quadratic factor, and that occurs twice, but it's a quadratic. Its numerator will be a linear, so gx plus h over x squared plus 3. But we had 2 powers of that, so I need one more term here, ix plus j over the quantity x squared plus 3 squared. This is the beginning of the complete decomposition of that single fraction into, what is that, 1, 2, 3, 4, 5, 6, 7 subfractions. Some of those will have zeros as numerators, and some of those will not. But this is the beginning of how you do that process. And this is what steps 1, 2, and 3 are right here. It's literally just saying, listen, factor that denominator. And for each factor of that denominator, you're going to have a fraction. And if that denominator has 3 powers, you'll have 3 fractions representing that factor. If that denominator has 1 power, you'll have 1 fraction. If it has 2 powers, you'll have 1. Trying to write 1, 2 fractions. So really kind of an okay way of doing this. Now the big question you're probably wondering is, do I have to do this? That's probably one of the first things you're wondering. And the answer is yes. And the next thing you're probably wondering is, how the heck are you going to find those? Yeah, in fact, Avi's just asking, how do you even know what the constants are? Or have we not gone over that? We have not gone over that. So today we'll just wrap up with the single statement that to find what these numerators are, and by the way, I would never give you a problem this crazy to find the numerators of. This is way too mean. But in general, the idea is very basic. Multiply both sides of this equation, because it is an equation, right? This is an equation. You would, 1, multiply both sides by the LCD. So if you look, the LCD is actually this entire denominator. So you'd multiply both sides by the entire denominator. And again, it would still be an equation, but then at that point, you could do what I call strategic substitution. And strategic substitution is basically choosing values of x to plug in to turn certain things off. And that's where we're going to pick up on Wednesday. There's no way I can even begin that discussion today. It's a big discussion. But for now, just know that each fraction you see can be broken apart into component fractions where denominators are the prime factors, powers of prime factors. All right. That's it for today. I will be back in about 10 minutes for office hours. I hope you guys have a wonderful day. It was wonderful seeing you guys. And yeah, I'll be back in 10 minutes.